When we look at modern manufacturing, everything from a jet engine to the phone in your hand, it all comes down to precision. We're talking measurements in microns. But what if I told you there's a secret language, a hidden code that decides whether these incredibly complex parts fit together perfectly or just end up in the scrap heap? Well, that language is called geometric dimensioning and tolerancing, or GD&T. And honestly, understanding it is the key to building the world we live in. So let's start with this really frustrating and incredibly expensive question. You've got a technical drawing, you machine a part to match it perfectly, it even passes inspection, and then when you go to assemble it, it fails. How is that even possible? The stakes here are just massive, and we're not just talking about a bit of wasted metal. Every single part that gets rejected means lost time, lost money, and maybe worst of all, a loss of trust. The root of this problem? It's often not in the machining itself, but in the language we use on the drawings to begin with. To really get to the bottom of this, we have to look at the traditional way we define parts. It's a method that seems really simple on the surface, but it's hiding a flaw that is just costing companies a fortune. Yeah, we've all seen this, right? A dimension is listed as, say, 10 millimeters, plus or minus zero point 0.1. It's how most of us learn to read a drawing. It feels intuitive. It feels clear. What could possibly be wrong with that? Well, here's the catch. That simple plus or minus is actually really deceptive. It creates this hidden geometric problem that can directly lead to parts being thrown out, even when they would have worked perfectly fine. The whole issue really just boils down to a classic mismatch. It's basically a square peg in a round hole problem, but applied to how we measure and tolerate parts. Okay, so here's the crucial disconnect. When you define a location with a plus or minus for your x and y coordinates, you create a square-shaped zone where the center of a hole is allowed to be. But now think about how parts actually fit together in the real world. It's almost always a round pin going into a round hole. A square tolerance zone just doesn't match the circular function of the part at all. And this is the heart of the problem. You see, parts that fall into the corners of that square tolerance zone might be perfectly functional, but they get rejected. Why? Because they're technically outside the biggest circle that can fit inside that square. We are literally throwing away good parts because of bad geometry on a drawing. So if the old language is broken, what's the alternative? Well, it's a system designed not just to describe size, but to describe the part's actual function. It's called geometric dimensioning and tolerancing, or GD&T for short. GD&T is a total mind shift. Instead of just saying how big something is, it describes its shape, its orientation, and its location relative to everything else. It's a language that captures what the designer truly intended, how the part needs to work when it's all put together. And this language, it's built on a whole foundation of precise, internationally understood symbols. Each one has a very, very specific meaning. Let's just take a look at an example. I mean, just look at how much information is packed into a single symbol like this one for position. It's not just saying, drill a hole here. No, it creates a perfectly cylindrical tolerance zone that actually matches the function of a pin. It controls exactly where that feature can be in three-dimensional space, all relative to other critical surfaces. It's designed to ensure a perfect fit. Okay, so that's the theory, but what does this really mean out on the factory floor? You know, where the rubber meets the road. How does switching to this new language actually save money and make better parts? The benefits are just enormous. Because GD&T focuses on function, designers can open up the tolerances on things that aren't critical, which makes parts cheaper and faster to make. It completely removes the guesswork, creating this crystal clear line of communication from the CAD model all the way to the final machined part. And, most importantly, it makes sure that if a part is in spec, it's actually going to work. So the end result is exactly what every manufacturer wants. Clearer instructions mean more efficient programming for those big CNC machines. Functional tolerances mean way fewer rejections. And all of that adds up to less waste, faster production, and a much healthier bottom line. But here's the thing. All of this efficiency, it really hinges on one thing: people. Adopting GD&T isn't some magic bullet. It takes training and a whole new way of thinking. This isn't just a technical upgrade. It's a communication upgrade between the engineers designing the parts and the machinists who actually bring them to life. You know, there's this really powerful idea that came up in a discussion with some engineers that gets right to the heart of this. No matter how perfect the drawing is, at the end of the day, the machinists are the ones who have to make the part. Their hands-on knowledge is just invaluable. And this quote, it just says it all, doesn't it? It perfectly captures the two halves of great engineering. First, you need that deep technical skill. You have to be fluent in GD&T. But just as important, you need those strong relationships that turn a good design into a great, cost-effective product. It's about combining that technical language with real human communication. So ultimately, we end up with this question. The language you use on your technical drawings isn't just a small detail. It's the foundation of your entire manufacturing process. Choosing the right one, a language of function, not just of simple dimensions, can literally be the difference between profit and a pile of very expensive, perfectly made scrap.